the numbers on the left-hand side and the right-hand side?
Basically, that's just a relative indication of volumetric soil moisture. So in that particular case, that's saying that 25% of that soil volume is moisture. You can actually have a soil calibration done and have it in mils of moisture per unit of soil and those sort of things.
I think it's for each of those lines, it's not a going up thing.
No, what we do here is that sometimes if you actually to stack these graphs on moisture, our deeper levels would be on the top because often deeper levels hold more clay, have more water, and it all gets confusing. So we actually stack them just by individual layers irrespective of what their total value is. So you're actually seeing the profile. Now, this is how we tell whether the plant roots are there or not, is that with plant roots, at night, the plant's not doing much, and so the soil moisture stays relatively the same. The next day, the sun comes out, the plant starts to transpire, so the soil moisture drops during the day, and then it's steady at night. It drops during the next day, and then it's steady in the night. Okay, so we see this stepping effect. And here, we've got relatively small stepping, getting bigger, and then bigger. Okay, and then it starts to get smaller and smaller. What's happening here is actually too much water in the soil, and the plant finds it difficult to get some water out. You need actually to have air in the soil to have good transpiration rates. So what we see is it starts to dry out. You reach these areas where you have maximum transpiration, and then down here, this is now pulling those last paper clips off the magnet. Okay, it gets harder and harder, and therefore each day it's able to get less and less. And when we flatline here, it does not mean that the soil has no moisture. It just means that that particular plant doesn't have the strength to pull any more paper clips off the magnet. Okay.
What we find in a lot of our soils, but I'm talking in our areas, is that when you come out in the morning, you'll find that everything's fresh and growing well, because it seems that there's a lot of moisture actually comes up through the soil profile, through reaction, up to the top during the night, and then the plant uses it again during the day. And is that
it's called diurnal fluctuation, and you can actually see that diurnal fluctuation. And a lot of some of this error, if you like, this noise in these graphs, which is really strong near the surface and gets less and less as you go down, is actually the effect of diurnal fluctuation. So it's more influenced at the surface because there's more exposure to the environment there, and so with depth you see less diurnal fluctuation, but it's certainly at the surface, and even down to 30 centimetres you see that.
Going on in sandy soils with clay subsoil down our way with delving and whatnot to cut through that clay layer, bring some of the clay up and work it through the top there, and I'm assuming that's part of the object of the exercise is to encourage that ability to be able to encourage that.
Oh yeah, but also catch it before it goes down. I mean, really what you're doing is bringing a lot more magnets, if you like, up to the surface. And so even the rain that does fall on top stays there. So rather than having big drainage and then waterlogging on top of that clay, like subsurface waterlogging, is that, just by making the profile more uniform is... no, I mean, delving works really well as long as you don't overdo it.
Sorry?
As long as you don't overdo it. So here, can everyone see here we have soil moisture infiltrating to 10 to 20 to 30 centimetres, it just touches on 30. And then you see here, this one starts to come down, that's the roots using the water. And as this one is starting to run out, we see the roots getting down to 30 centimetres. And as 30 starts to run out, we see 50 cut in. Can everyone sort of see that? Yep. You notice when we have a little bit of rainfall at 10, that the ones at depth rest. Okay, plants, like everything, like to do the easiest thing as possible, and getting the moisture from the surface is much easier than bringing it from depth. And this is very important because we're going to look at that, why that's important later on. So here we've got our drainage going on, it's a bit over capacity, so it's all full water going down. By here we've got plenty of available water, great conditions. Here we've got some available water, but it's getting tougher, and here there's water, but the plant can't get it. That's it. All right. In terms of repeatability, just what we're seeing here is this at 30 centimetres is starting to come up. Okay, that means there's water coming from above. So the cation exchange from here is accepting water from above, and the overall moisture content at that level is increasing. So this is draining. You notice that the graph at this point here, when this starts to reach, still keeps going up for a while, that's overcapacity, meaning that the soil moisture at that stage is over what it could naturally hold, but simply because it's raining, there's more coming in than it can drain down. So that's where we start to see things like waterlogging occur. If we draw that line across, we can assume that at that same point, that's when it's going to start to reach that capacity again and when it's going to start to drain. And lo and behold, that's exactly when this one starts to take off again. Okay? Now the thing about this is that some researchers are just talking before that say soil moisture probes aren't any good because they're not exact. The exactness doesn't matter as much as the repeatability. If you know this is where the wheat wilting point is, long as next year it's in the same spot and it's the same probe, it'll come back to that point and wheat will still wilt again at that point. Whether that's 42 mils of soil moisture or 44 mils of soil moisture, I think is not really the issue. The issue is having a relative guide to know how your moisture is sitting in your profile and where it's at. Losing moisture, okay. So I want to talk about what I call the garden hose effect. And if you think about a garden hose, when you buy it brand new, it's empty, it's got a lot of air in it, you click it on, you turn on the hose, and it takes ages for the water to come through, right? But once it's full, you turn on that hose and the water comes straight away. It's not the same molecule of water, but the whole thing's pushing, right? So here at 10 centimetres, we see 10 become full. At 20 centimetres, 20 goes up and becomes full, and you can start to see 30s creeping up, more rain here, and rainfall's creeping up. That's basically the opening break, April for us, 2009 I think, yep. Keep going along in that season, 10 and 20 are full, so they mirror each other, the same as if a garden hose was full. So a metre along the garden hose and 2 metres along the garden hose is going to do the same thing if you're turning on the tap, right? And you notice that then 30 is in the swing of it, and 30 is doing it, and then 50 becomes full, and now it's in the garden hose effect. Then down here, even here at 70 centimetres, that reaches a capacity, and now that's in the garden hose, and even at 100 now we're seeing that deep moisture start to fill up. Okay, this is really important, and I'll show you why in a while, because we're going to talk now about something called a summed graph. So far we've been looking at the individual layers. What we can do is add all those layers up together to give us one total look at the profile. And some of the places that's been used in the past, this is onions data, but here the onions are still in vegetative growth, so they're still using a lot of moisture, but by the time they get to their reproductive phase, they just, naturally the plant uses less water, and so we're able to see at the same soil moisture level that in the reproductive phase, in the vegetative phase, it's using a lot of water, but in reproductive, even though the water's available, the plant itself has changed its physiology. It doesn't want to use the water. This is a cotton plant, small here, very small plant, but as it gets bigger, its capacity to have canopy and root system grows. It's getting hotter, it's using more moisture. So through our whole profile here, we have very small water use, to big water use, to larger, to very large water use. Okay, so through the whole profile, we're looking at the whole drawing potential. And a pasture, this is a hot, windy day with lots of moisture being used compared to 2 cool days. Okay, so through that whole sum graph, we're able to look at a whole lot of different environmental and plant characteristics. Now, this is 2 summed graphs looking at 2 separate years of 2007 and 2008. The first thing I'd say is that basically the in-season total rainfall of those 2 years were very similar. They were both drought years, but we had 2 significantly different outcomes in grain growing. Now, if we just focus in on this key period here of August to November, which is really that late nitrogen application, grain marketing type of decision type of time, and we overlay those 2 graphs, you see 2007 is pretty linear, okay, so there's a bit of noise in the data, but it's fairly a straightish type of line, whereas 2008 is more like a slippery dip, okay. Now, it took 9 days to get through that moisture from 155 mils to 145 mils in 2007, and only 3 days in 2008. Okay, that's actually got to do the positioning of the moisture. In 2007, we actually had some summer rain, a bit of carryover of moisture at depth, and because the moisture is so hard to get from depth up to the head, it's actually being self-regulated because it's harder. So it can only take out a lot less. In 2008, what we had was crops growing with a bit of rainfall falling on it, and then that was being transpired away because it's near the surface and it's easy to get. Then the next rainfall would come just in time, so there was no crop stress and it always looked moist in the paddock. Okay, then that would be transpired away quickly, and then it would happen again, and everyone's thinking, oh, this is all looking pretty good. But remember, we've actually extracted all of the deep moisture in 2007. There's none left. So when spring came around and there was no more moisture, everything got guzzled away quickly. So compared to being at depth where it was safe and secure for a while, the young roots couldn't get at it, and as they got at it, it was hard to bring it up, so it was self-regulated. We had some yield compromised, but quality was still okay, so the grain that was set basically filled. In 2008, we'd actually transpired almost all the moisture for the season in building a canopy, and suddenly there's no rain and there's nothing left underneath, and so lo and behold, what happens? We have a lot of screenings. So how can we look at the soil moisture profile and start to determine whether we should be applying nitrogen at a certain time, whether we should be marketing our grain, and what's our risk of screenings? Okay, and I think that because that was so widespread in 2008, I still think we've got a fair bit to learn. Now, is everyone comfortable with that? I know it's pretty quick to get over some of that.
2009, what about 2009 when we had that 10 days in a row of 40 degrees heat in November? Well, that was sort of later area and that's a fried us.
Sure. I mean, there's got to be other parameters which give you grief, no doubt, but the soil moisture is still one that can tell you, give you some reflection of how resilient you might be against that grief. Okay. And for example, I actually believe that we're actually going to do reasonably well to grow in lower rainfall. I'm not so worried about the rainfall change. To grow reasonably reliable crops in lower rainfall, at least in South Australia, the area that we're experienced in. I think the big issues are the intensity of what we would call event days, like a big frost. Okay, like that one day in August where we had 36 degrees and a north wind during flowering. I think they're much bigger risk than overall lower rainfall. Okay, but that's a different issue. And if you get an event, then knowing your soil moisture may or may not help that. It might not help it at all, okay? But in general terms of having a robust reasoning behind why you're putting on nitrogen, if you don't have any subsoil moisture, but even if it still looks good at the canopy level, I reckon you've got to be pretty game to go and put 80 kilos of urea over the top of something like that. Really? Because, what's going to finish that crop? Yet if you do have reserves that are yet untouched at 60, 70, 80 centimetres, and you know that the roots from previous history can get down, there's no subsurface constraint like a boron layer or what have you, that's a different risk profile completely to putting on nitrogen. You're not as subject to the late rain, but an individual event like a frost could still strike you.
Greg, just on that note, we were talking about briefly before, comparing this measured with model, and so when we've got yield profits out there that does those sorts of calculations,
yep.
which essentially is another way of looking at that.
Yep.
And I guess, but I don't think yield profit actually makes a distinction between moisture and the profile, the location of moisture.
No, and I think it's super important. Yeah, I think it's critical because if it's near the surface, it's going to be guzzled away and it's going to go early. If it's deep, it's going to be regulated and it's going to go late. And that's why, when people say, oh, deep moisture is worth X amount in the French Schultz sort of thing, like indicatively that's where people's thinking is getting to. It's just that simple. I think it is just that simple, is that it actually is deep and therefore the young roots can't get it, and its actual transpiration is going to be regulated because of its depth, and therefore it's going to be drip feeding it through filling. And that moisture use therefore in terms of the physiology is completely different, and I think that's a much better risk profile than having